Okay.
So finally, looks like worse. But you will take out your. Or should. Are you going to say something? I start.
So good afternoon, everybody.
Good afternoon, sir.
Good afternoon. We're happy to have you here, and we're happy to have Professor Sanpera, all the way from Barcelona, here with us. She's an expert in quantum information, and she's a physicist and expert in quantum information. So she'll be taking us baby steps that will be able to become experts in quantum information. The way they usually say it is from 0 to hero. So we hope that this lecture should take us from 0 to hero. So over to you, Anna.
Okay, thank you. Thank you, Molobu. So I was saying that I would do a very simple lectures, but I'm going to talk this year about quantum computing. I wanted, but first I'm going to ramp up. Okay, so these are 4 lectures, and the idea is that going to work. Yeah. Okay, so this is going to be the first lecture, maybe a second, about the basic formalism of quantum information. So I will assume that you know more or less a little bit of quantum mechanics, but I wanted to say what is important in quantum mechanics for quantum information. And then I want to talk about what does it mean to solve problems. Okay, what is the complexity theory, and why quantum computers are expected to work better, and why there is a lot of people putting money in quantum computers, and which kind of problems they can be solved and which kind of problems cannot be solved. Okay, so there is a little bit of a hype that everything can be solved, but this is not like that. So there are problems that can be solved and problems that cannot. And this is what I would like to say in the last 2 lectures. Okay. So, I mean, although you probably have done quantum physics, okay, when we do quantum information theory, we have a little bit, of course, we use quantum physics, but we have a little bit different perspective on that. Okay, and we take that quantum mechanics or quantum physics is just mathematical description, okay, of our world. Okay, and that together with the postulates of quantum mechanics, it tells us how to describe, manipulate, and measure quantum systems. This is the only thing that we can do with quantum systems. We cannot do anything else. Okay, we can kind of prepare. Okay, we can prepare these states, these quantum states. Then we can manipulate them, and we can get information measuring. And in particularly, we will use only the postulates that they are helpful for quantum information, which will be that they are relevant to codify information. So what we want to do is to codify information, whatever information, so everything is information. We want to manipulate this information, we want to send this information and decodify this information. Obviously, this is the basics of quantum communication, but of anything. Okay, so if I want to do quantum computing, I have to prepare some states, I have to manipulate these states, and at the end I have to measure. So there is no other option. So these are the only things that we would like to do. So, and when we do quantum info, what we think is that we have a quantum state, and this is a mathematical object. So a quantum state, it's not a physical object, it's a mathematical object that describes all the probability distributions of any measurement I can imagine in the world. Okay, it has to do that. So I'm going to describe a system, whatever it is, but I don't care now all the system. So I'm going to describe I have a mathematical object that describes a physical system, and it has to be coherent in the fact that whatever measurement I'm going to do on this physical system, okay, this mathematical object has to give me an agreement with that. So this is how we think in this way, and it's very related to the experiments. Okay? So it's mathematical, but it's very related to the experiments. So if I do an experiment and I have a result which doesn't agree with that, that means that this object that I have done, it's not correct. Okay? And I can summarize very simple what is quantum mechanics, at least for me. Okay, so super simple. But this is everything that one needs to know about quantum mechanics. Okay. And in quantum mechanics, we have three things. I say we have the state, we have the manipulation of the states, and we have the measurement. There is nothing else. Okay? In any quantum mechanics, it can be much more complex. It can be describing systems, semiconductors, which is very complex. It can be describing quantum computers, which will be very complex. But at the end, everything is these three steps. So one can understand quantum mechanics like that, saying that they are microscopical objects, which are described with an object mathematical, which is a quantum state, which are represented by vectors. Of course, they can be also density matrices, but the thing which is inside is the same. Then I can have transformations of this physical object, okay, or of this mathematical object. And these transformations are operators. Okay, and I will explain what are these operators. And then I have to measure, okay? And measure are also represented by operators. And this is why quantum mechanics is such a compact thing. So I only need to define what are operators, okay, and what are vectors. And transformations of vectors, we will see. I have a vector, psi, which is a quantum system, and I will have a transformation given by an operator. Normally, we put it in alpha hat. Okay. And that will give me another state, whatever it is. So it's very easy if you see like that an operator is just something that transforms vectors into vectors. This is a matrix. Okay. So quantum mechanics is an algebra of matrices. There is nothing else. One has to know how to work with so this is Heisenberg original description, but we can write it always like that. So we only need to have a good description of what are operators, a good description what are measurements, a good description of what quantum states, and that's it. And the complication in quantum mechanics is because it's, as we will see, many things are not intuitive and we have to understand it. Okay? So I'm going to just review today very briefly the things that we are doing and how do we work in quantum information. Okay, so the first thing is, and we will see it. So I have said that quantum states are represented by vectors. Okay, and this is the postulate, the first postulate of the quantum mechanics. Okay, that which is important here is that associated to each isolated system, which in real life this doesn't exist, or very hardly exists, because we cannot not isolate anything. So everything is in contact with something. So isolated means that there is, I have, for instance, a quantum system. Imagine an atom of hydrogen that doesn't interact with anything. Okay, absolutely with anything. That will be to be isolated. But if it interacts in something, because I have it in a box, I have to pull it, I have to have this atom and so on, then it's not isolated. But ideally, if my system is isolated, it's described by a complex vector. So the system has associated a complex vector space, which has a scalar product, and this is what we call the Hilbert space. Okay, and this system is completely determined by a vector, which is unitary. So there is nothing else. So for instance, if the dimension, and normally in quantum information, we work with very simple models, okay? Because physically also it's possible to do it. So the experiments can work like that. If the experiments wouldn't work like that, we wouldn't do it. But we work with the most simple Hilbert space, which has dimension 2. Okay, so it only has 2 degrees of freedom, and this is a qubit, because it's like a bit. Okay, in classical physics, which is a 0 or a 1, a qubit. It's a quantum system that can take 2 values, 0, the quantum system, and 1, plus all possible superpositions, because this is the first thing which is highly different from classical physics, where we have all possible superpositions. So a priori, a state psi can write it like a combination for a qubit of alpha times 0 plus beta times 1. Alpha and beta are complex numbers, but since it has to be unitary, we know that the modulus has to be equal to 1. So it's a very simple description, okay? And the 3 or 4 important things of the postulate 1 is, 1, that it's isolated. If the system is not isolated, I have to describe with a density matrix, but I don't want to talk because it's the same, it's more formal, and it's better to do everything with a density matrix, but I prefer to do it with states, okay? The other thing important is that there is a complex vector space, so it's not real, and this is important. Indeed, It's very important. So some people try to do quantum mechanics with real numbers. You can try, you say why we need to have complex, and then in very many cases it doesn't matter, but in some cases you get inconsistencies. So it has to be complex. And that there is a scalar product. This is fundamental because that tells us which is the length of this vector. So it has to be unitary, and I have to measure which is the length of these vectors. And it always has to be the same, so it has to be unitary, and the Hilbert space, which is nothing, infinite dimensions, which is normally what we do in quantum information, not always, but we have a finite dimension, so the Hilbert space is finite. It's the same to have a complex vector space or Hilbert spaces, identical definitions, okay? And the scalar product, it's very important, okay? So this is, it's embedded in the first postulate, okay? And then we will see, I would like to convince you that we can understand quantum mechanics always like transformations. So we all know what is scalar product, but now let me put it like that. Scalar product, it's a map. Okay, so a map is an operator, so always it's the same. It's a map which takes two vectors, psi and phi, okay, and makes an operation of them. And as a result, it's a map that it goes from two Hilbert spaces to a complex number. This is a map. It's an operator. Okay? And we know that it has to fulfill these things because if not, we reach to incongruences, that it's conjugation symmetry. So if we do the complex conjugate in the other order, we would have a complex conjugate. Okay, so it's linear but anti-linear in the second argument. It has to be linear, okay, in this argument. So if I do it in the second argument, it's linear. So it's an operator which is linear. Okay, and it has to be semi-definite positive. Why? Because that measures which is the norm of this vector, and the norm, the length of a vector has to be something which is positive. Okay, so or it can be zero. But if it's zero, that means that this is the zero vector, which exists because quantum states are mathematical objects. Remember, okay, we defined it with a mathematical thing. So if we have these three things, we have already completely defined what is the first postulate, which the first postulate simply tells us that quantum mechanics, the quantum systems, they are described by vectors. These are the vectors that they work there with these conditions. Okay. And this is very important also because, as I say, we have to define the scalar product because we have to define which is the length of a vector, or which is the superposition between two vectors, or how two vectors are similar. So two quantum states, how similar they are one to another. Well, I need to compare them, so I will compare it with the scalar product. And these are two inequalities which are exactly the same like in classical physics for real vectors, okay, which are super important because this is the geometry, which is the Schwarz inequality, which tells us identical that in real dynamics, so that the scalar product of two vectors has to be always smaller or equal than the length of each vector. No? It's always like that. And the triangular inequality, which tells us that the sum, okay, the length of the sum of two vectors, it's always equal or smaller than the sum of the sides. No? This is triangular Pythagoras, okay, so to say. And the equality means that the two vectors are on the same length, or in geometry, our geometry is the triangular, so the triangular inequality. So the sum vector A, this is vector B, and this is A plus B. Okay, and A plus B is smaller than A and B, the sum of A and B, and it's only equal, obviously, if this is A and this is B, so they are parallel, then A plus B is the same length as the length of A. So it's exactly like, it looks like that, but it's like classical. Okay, so all these concepts are transformable. Okay, so what we do in quantum mechanics, because it's very in quantum information, because it's very useful, it's that we are going to use always this Dirac notation, which are Bras and Gets. Okay, and why? Because this is the most easy way to operate. So in quantum mechanics, normally when you do quantum mechanics, you do first quantization, and you have wave functions. Okay, we are going to forget about wave functions. We are going to put everything in this Dirac notation. Okay, and then you have second quantization. I don't know if you have done this, but second quantization, what do you do? Second quantization, speaking very broadly, it's doing the following. In first quantization, in classical physics, we distinguish between two kinds of objects. Okay, objects, material objects, and fields. Okay, electromagnetic field, gravitatory field, etc. Okay, and first quantization, the matter we quantize, we make wave functions. Okay, and then the fields are separated. And in second quantization, we say, no, there is not this classification. Quantum physics tells us there is only a kind of object. So we quantize everything with creation and annihilation operators. For the electromagnetic field, for photons, we have creation and annihilation operators. For bosons, it's matter, creation and annihilation operators. For fermions, which is precisely the most important thing in matter, creation and annihilation operators. So second quantization is conceptually very important because it says, no, everything is the same. Okay, it has different properties, but we can describe any quantum system in the same way, creation and annihilation operators. And here what we are going to do is to use a kind of Fock state, which is similar to second quantization, which is this Dirac. And it's very easy. Yes, yes.
If there's a d minus 1,
Yes.
is to be 0.
Because this is a notation. This is a basis, okay? This is a basis, and I can order it. So if I have a Hilbert space of dimension D, I can order it first element of the basis. So it's a complex vector space. There is a basis. The vectors are orthonormal, and normally in quantum we like to put it from 0 to d minus 1. You could put from 1 to d. Doesn't
No,
matter.
like I mean for d minus 1,
Yes.
the vector is to be 0.
Sorry. Yes, you are completely. D minus 1 is 0, the first and everything. Yes, this is an error. Thank you. Yeah. Okay. Absolutely. Yeah, I make a mistake. In d minus 1 is 0, 0, 0, 0, and the last component is 1. Okay. So, and then if you have this basis, this is the basis that we use. Okay, and this is called the computational basis. Why we use this basis? Because it's simple, but we have to be careful because depending, sometimes we will have another basis which is better, like it happens in classical physics. Okay, so in classical physics, we don't say it, but we say which is the basis that we use. No, so when I want to do something, I fix the basis because I say, okay, this is my basis, X, Y, Z. But obviously, I could make another basis. That would be I prime, Z prime, and X prime. And if I want to define where is this object, I have to say which basis I'm using, because if not, it will be different. Okay. So in quantum mechanics, it's the same. So we fix a basis, which is this computational basis, and sometimes we will have another basis which is better. We have to say in this basis that it's like that. Okay. So for instance, if I want to do a transformation, okay, this is a transformation, no? Because I have rotated by an angle theta my basis, I have to say with respect to which basis, because if not, that will be very confusing. But it's exactly the same. So for any state, okay, any vector which is in the Hilbert space, we write it as a linear combination of the elements of the basis. For this basis, fantastic, and for a qubit, this is what we did. Okay, for a qubit, which is the element, the basic element of quantum information, we will do the same. As the psi, it's alpha times the vector 0, which is the 1, 0, plus the p times the vector 1, which is the 0, 1, and I write it in these different ways, alpha, beta, or whatever. Okay. And we can do the same now in this notation. We have the gets, which are the vectors, and now we have to define the bras. Okay. And the bra, I take a vector and I just switch it and put it as a file. This is a bra. Okay. And add the vectors of the dual space of the Hilbert space. Okay. And I would define it like that. So if I had my element of the basis, which was 0, now and now how should I take this out? You know, hide video panel. That's it. Yeah, thank you. So I can do the same. I can do the same for the elements, and I need to do that. Okay, I have to define the whole quantum mechanics in terms of bras and gets. So I will define that the bra it's just, I have a basis. So this is the basis for the dual space of the Hamiltonian. Okay, and this you are used to do it because this is how we do the scalar product. The scalar product is an application which takes a bra, it takes a ket, and gives me a complex number. Okay, so, and this is exactly how one can understand it. The scalar product, we will say it's a bracket. Okay? We will not say anymore, so we will say brackets and a bracket. And what else? So this is the first part. This is postulate one. Okay, and what is important here to remember is simply that we need a basis, which is the computational basis, that we use qubits, which has their own one, very simple. Okay, that the vectors have to be unitary. And now we want to know, well, what do we do with these vectors? Okay, so we have seen that these quantum states are represented by vectors, transformations are represented by operators. Whatever I can do to my system, so I have any system, I have an electron or I have an atom, and I want to do something to this atom. I want to move this atom from here to there. This is an operator, okay? It's a translation operator. I'm considering the spin of the electron, and the spin is pointing in this direction, up, and I wanted to flip it down, so I have to put a magnetic field. This is an operator, okay? Mathematically, this I'm going to describe it with an operator, and I'm going to go to the person which is an experimentally, I say, okay, I want to apply this operator, which this operator is, if I had no magnetic field, apply a magnetic field, and I will write it as a, this is like that, okay? So my operator will show exactly all the transformations of my state, and if I measure, if I have defined well, and I have described how is the state, when the experimentalist measures, she or he will tell me, I have this result, which I have to be able to do it theoretically, okay? Because I'm describing a quantum state which has to give me all probabilities. Okay, we know that we will see it in measurement that it's probabilistic. It has to give me all probabilities of all correct probabilities of any possible experiment that I can imagine. Of course, I have to assume that the experiments maybe they will make an error, no? And then it will not be correct. It's because there is an experimental error. But if not, it has to give me everything. Okay. So how are these operators? Well, the experimentalist? Yes, it will give averages, but my state with doing the averages has to give me the same result that the experimentalist will find. Absolutely. But assuming that there is a pure state, and I can do a single measurement, okay, which is this is ideal, I also have to get the same. That's not the average, but the individual. No, we will see the max number. Okay. And now we want to do transformations, and I like to think in quantum mechanics as a very simple thing. So I say transformation is an operator which transforms vectors into vectors. Okay, and of course I can transform a vector which lives in a Hilbert space to another vector which lives in another Hilbert space. Okay, what does that mean? Okay, so can I do a transformation? Well, we will see what it means. No, a priori sounds a little bit strange that if I have. But mathematically, this is completely right. So if I have a Hilbert space, which is initial Hilbert space, which is the same as the final Hilbert space, I know that my operator has to be square matrix, okay, because I will have as many components. But imagine an operator doesn't have to be represented by a square matrix. Okay, it can be a bigger space, or it can be that I go from a bigger space to a smaller space with my operator. Why? Because imagine that my operator, for instance, is that I project my quantum state in some superspace. Okay, so I have a quantum state which lives in a Hilbert space of dimension D. Okay, and now I make an operation which is projecting in a dimension D prime. This is completely right. No, classically, how we will think that? Imagine that I have a three-dimensional object, and I project, which is a projection of this three-dimensional object in my screen here. So I go from 3D to 2D. Is this a correct measurement? Yes, why not? No, so I have this which is three-dimensional. Now somebody, I put light, okay, and so imagine that it is dark, and then I will have a shadow here, okay, which corresponds to this object. What I have done physically I have transformed something which was 3D. I have projected into a screen which is 2D. Okay, so this is what it means. So in quantum mechanics, we can also do that. And if we do that, okay, that means that the initial state Hilbert space and the final Hilbert space, they don't have to be equal. Okay? Or I can do measurements, or I can do things like that. Okay, so normally we have to distinguish and we say, okay, an operator, okay, it's a transformation that it goes from a Hilbert space, input Hilbert space, to a final output Hilbert space. Okay. And now, super important, because quantum mechanics is a mathematical formalism, which is an algebra, some matrices, but it's linear. This we know, our world, it's linear. If it was not linear, it would be super complicated. And so this is very important. Whatever it is linear, and linear means like it means in any vector space which is linear, that if I apply my operator to the sum of two vectors which are multiplied by some scalars. In this case here, the scalars are complex numbers. That doesn't matter because it's a vector field over the complex numbers instead of the vector field over the real, which is what we do normally. Okay, it has to fulfill that. And if we want to know, I say, okay, of course, an operator of it's a matrix, so it depends in which basis I have described my system. But that will be very complicated, but it's enough that we know how this operator acts in the computational basis, in one basis, and then I know how it acts in any other basis. So it's enough. Okay. And so, and this is the reason, since a linear operator, well, indeed, and an operator also, but since a linear operator maps vectors into vectors, we know that an operator is a matrix. And the other way around, if I have a matrix, which it doesn't have to be a square matrix, so here it looks a square because I put it like that, but it's not. So I have n files and n columns. Okay. So I have to, if I have, okay, this, I can associate it to an operator. So for instance, I can think that a bra, I can think like if it's an operator. What does it do, this operator? This operator is an operator, the transformation, it's a matrix which has one file and n columns, okay, and transforms a state which was in the Hilbert space is a transformation, okay, into a complex number. Right? I can think it like that. There is nothing bad. So what I'm doing these things like that because I wanted to tell you that we can do in quantum information, we understand quantum mechanics very mathematically, but very simple, all right, with the elements, with the essence of the things that they are there. Okay. And I can do the same, no? For instance, I can think, and I will have to do it because it will be the way that I will do that. It's the same. I have defined what is the scalar product, which is the internal product, but I can also do the external product. Okay, it's also an operator. So if I have two vectors that they are in two different Hilbert spaces, the external product, what it's trying to do is a map again. So for me, an operator, a transformation, a map is the same. I take a vector which is inside in the Hilbert space 2, and I apply this, which is the external product. Okay, and I end up. How do I understand that? I say, fantastic. Okay, so this is this thing, which is it's an operator, so it's a matrix. I apply it over here. Okay, but now I know what it's the scalar product. So this is very easy to see that this is exactly like this guy over here times the scalar product. Okay, and the scalar product is a number. So at the end, I end with a number times sign. So I have moved from x2 or h2 to h1. So, and if I change the scalar product, I will do the other way around. I will make a transformation from h1 to h2. Okay. And of all these operators, the one that we will be using all the time, it's very trivial, but it's fundamental because this is the one that allows us to change everything. It's the identity operator, which is an operator that acts between the same Hilbert space because it maps each state to each set. Okay, it's trivial, but we need to use it all the time. Okay, so for any basis, we can write this identity operator like that. Okay, and this is the I would say one of the most relevant mathematical tricks. Because whenever I don't know how to change basis or whatever, I will write always the identity operator. This will help me to change basis to go. So it's fundamental. So in case of that we don't know how to operate, we insert the identity in all places, and then we know how to do it. Okay, so it's very important. Okay, so if I have defined that it's a linear operator, which is a matrix, and I can write it in the matrix form. In quantum mechanics, we say that we have also the adjoint operator, and this is fundamental. Okay, and what is the adjoint? It's the dual. Okay, so if I have an operator A, which goes from H input to H output, and it's the normal, I can always define an adjoint, okay, which goes from the output to the input. Okay, and how is this adjoint? Well, you all know, and this is the fundamental thing of quantum mechanics. So it comes from the first postulate, if you want also, what it has to do. So it has to transpose the expression of the operator and complex conjugate. Okay, so what do we have to know about linear operators? Well, we have to know about linear operators that there are matrices, that the dimensions of the matrices depends on I and J. So if there is the same dimension, this is a square matrix. That for a linear operator, I can always define what is the adjoint of this linear operator, and that they fulfill the conditions of quantum mechanics. Okay, so if I have now the product of constant times an operator, this is, I have to be careful, the constant has to be complex conjugate, and I have to change always the order, if not, nothing will work. That the sum, the conjugate or the adjoint of the sum of two operators is the sum of the operators, that the multiplication, the adjoint of a multiplication goes the other way around. This is fundamental. And this is fundamental because the matrices, as you know, matrices not in quantum mechanics, matrices in general, they do not commute. Okay, so when I do the products, I have to be very careful. And the other thing which is very important for everything that we are going to do there is a lot of properties of matrices, we know, but here for us in quantum mechanics, and in particular here, it will be very important. One thing is that if I have a matrix, which is, okay, well, this is not correct. Okay, what I have put here, but it's not correct. For any matrix, which is or any operator which is Hermitian, so it's equal to its complex conjugate, I can always diagonalize. So of all possible bases which are in the, remember that the basis is just a change, a rotation, all right? So of all possible bases, how many bases do we have? Infinite. Okay, so in our space, how many bases do we have? Well, they are infinite, no, because I can do infinite rotations. So there is infinite bases. It doesn't have any sense to count. But if my operator is special, okay, there is a unique basis, in which this operator is diagonal, and this is super important. Okay, so and this is what it's called normally the spectral decomposition. So I can write this Hermitian operator, okay, which is equal to the adjoint, like the sum of some numbers, and this expression of here and projectors, which are the eigenvalues, and they have to be real, and the eigenvectors. Okay. So everything that I have said, let me see how it is for qubits, which is the things that we are going to use. Okay, for qubits, I have my basis, computational basis, the 0, 1, my states, psi, which is now instead of putting alpha and beta in quantum mechanics, normally in quantum info, we put psi 0 and psi 1, that doesn't matter. Okay, complex numbers. The bra is the same, I have to complex conjugate and change gets by bras. The bracket is the scalar product, which is like that, it's a complex number. It's unitary, which means that the bracket of a state with itself is 1, and I have these linear operators, okay? A, which is like that, A dagger, which is complex, conjugate, and transpose, 5 columns. And I can write it, and normally I will write it like that, okay? And then you see that this expression depends on the basis, okay? So here, the expression of A is in this computational basis, but I can have the operator in another basis. So when somebody gives you the expression of an operator, you have to ask, first of all, in which basis it's written. Okay? This is fundamental. If not, you cannot do anything else. Okay. And before finishing, because I just want to put the notation that I'm going to use for this case before going to the others. So there is three kinds of important. There are many operators, but for us important there are three. No, the self-adjoint, which is a T there, which are admissions, which we know that describes some properties. The unitary ones. So this is already another postulate. So these are the postulates of quantum mechanics. Okay? Very summarized, but they are like that. The unitary operations. Okay. So which are these? These are operators, special operators that they feel that the adjoint is the inverse operator. So this is the postulate of evolution. The evolution of an isolated quantum system also always follows a unitary. And the self-adjoint, this is another postulate of quantum mechanics. If we want to know properties about a quantum system, we have to apply a measurement which is self-adjoint. Okay, this is the properties that we can learn about the system. And the third one is the measurement operator, part of the measurement operator, which are projectors. These are operators that square are equal than they self. This projects in a subspace. Okay? These are the three most important kinds of operators that we will use all the time. Okay?
Why measurement operators?
Because any observable, okay, any observable is an adjoint operator. There is a basis in which I can write it for that reason of here, although the most normal measurements will not be like that, okay? But any adjoint, and this is what I say, A has to be equal to A data. I can always find a basis which is like that, and these are projectors by definition, because these are is a basis. Okay? Oh. But this is not the measurements that we are going to do normally, okay? So normally in the textbooks, they say the measurements are projected, but there are more measurements. And this is something which is very important, which is called POVMs. And this is something that we have to do. Okay? But this is like that. Okay, and in qubits, so which is, I'm saying, 99% of everything which is done in quantum information is with qubits. Why? Because it's easy to manipulate, and because experimentally it's very easy to. It's difficult, but now we know. So you take an atom that it has many levels, and you just select two of these levels because you have a laser that only links these two levels. Okay, so in the way that you are doing, but only links. So if I have a laser which is monochromatic, so it has only one frequency, I can have my hydrogen atom which can have many levels, okay, something like that. And here is the continuum. Okay, but maybe if I'm able to have a laser which has this separation, okay, I can forget about the hydrogen atom. I say this is a two-level atom, right? Because the other levels, they will not be connected, okay, with the light. So I will manipulate it with light, and this is how they do it. Okay, so if I only have to worry about that, okay, I don't talk anymore about hydrogen atom. I talk about the two-level system. Okay, this is what we do in quantum mechanics or in quantum information, 0 and 1. Sometimes we have to use more, and still we don't know. Okay, so we are in so we can do everything, many things with two-level atoms. So it doesn't matter how the spin up, spin down is the same, whatever. But in spin, we know that we will have only these 2 degrees of freedom because we put a magnetic field. But also there are things that we will need to have more levels. But I have to say that quantum information is very much developed. Why? Because it's very much based in information, and information we know it's done everything with bits, okay, 0 and 1. So we know that any number that we use, we can write it as a sequences of 0 and 1s. We know that our computers, they work like that, okay? We don't use 10 digits, we use 0 and 1s, okay? Why? Because this is enough, because this is the theory of communication that Shannon did, and we say everything in 0s and 1s works. So when we do quantum information, we do it with quantum 0s and quantum 1s. For some things, we will do others, okay? But for many things, it's enough. And in this space, which is C2, okay, Hilbert space of dimension 2, there is a fundamental thing, which is the Pauli operators. Okay? Why? Well, because any two-dimensional adjoint operator, which are the things that we can measure, can be always be written in terms, is a linear combination with real numbers of the Pauli basis. In the Pauli basis, Okay, so it's the identity, yeah, sigma x, sigma y, sigma z that we have seen always and we are using always. So we could have chosen another basis, no? Because if I have a matrix which is 4 by 4, I could have said, okay, okay, so here there are two things which are important, and I would like that maybe we stop and think a little bit. And this is also very important in quantum information. So what we have said is we have vectors, and now we have operators that transform vectors to vectors. Okay? But what we will see is that vectors, these operators that we have, also can be considered as vectors in a larger space. And I can put what we call super operators, which transform operators into operators. Okay? What does that mean, what I'm saying? Well, I'm saying the following. If I have a matrix 4 by 4, any, not this one, any matrix, okay, sorry, 2 by 2, which has 4 elements, any. Okay, so I take a matrix 2 by 2, which has entrance A, B, C, D. Okay, and it's obvious that this I can write it in the terms of a basis. No, so I say I have this A, B, C, D, and you all will agree with me that this is A 1 0 0 0 plus B 0 1 0 0, okay, plus C 0 0 1 0 plus B 0 0 0 1. Okay, so any matrix, I can write it as a linear combination of these 4 matrices, which form a basis, okay, in the space of matrices of dimension 2 by 2. Okay. In particular, the ones that they are here, which are the Pauli matrices, and we use it constantly because we represent with that the spin operator, the rising and lowering operators, everything. Okay, they are a basis. Okay, a basis with a real component for any adjoint operator in 2 by 2, and they are super important. On top of that, they are unitaries. Okay, so if we calculate the transpose, we see that it's equal to the inverse. Therefore, okay, they correspond to also operators of evolution. Okay? Because a unitary transformation means that this is quantum mechanics is unitary. Okay? So anti-unitary. So these operators are very important.
Excuse me.
Yes.
The previous slide, the notation has the revision the R1.
Sorry, this B means that it's a vector Bx, By, Bz. I wanted to put it like that, and sigma, when I write it like that, it's a vector of Pauli matrices, sigma x, sigma y, sigma z. This is a compact way to write it. Okay, so which corresponds here is that I have that my operator A can be written like a real number B0 times identity plus Bx sigma x plus By sigma y plus Bz sigma z.
What type of
It's a scalar now of 2 vectors. Okay, and real vectors, I would say, like 2 numbers. It's like 8 times 3. Exactly the same. If I give you the multiplication of 2 vectors in 3 dimensions, this is ax bx plus ay by plus az bz. But a is the vector ax by az, and b is the same. Okay? So it's a little bit funny because now this second vector is a vector of matrices, but it's fine. Calculate. It's a vector of matrices. So we are almost there, and we have still to define something that we don't do normally in mathematics, is how we define the function. And we will use that very often. Okay, so if I have a function of a number, I know very well f of x equal to x squared, I know what it means. So what it means, f of a matrix. So if the operation is square the matrix, is the same. I square the matrix. Okay. But there are things which I cannot do. Okay, so for instance, I give you a number, well, I can do. Imagine that I say calculate the log of a number. Okay, you can do it if the number is positive, no? Because it doesn't exist the log of a negative number. But now if I say calculate the logarithmic of a matrix, well, what is that? No, this is very unpleasant, no? Because what doesn't mean the logarithm of a matrix? No, I mean, I understand what it's to square a matrix, but the logarithm of a matrix, I don't understand it. And we shouldn't understand it. because it's not something which is defined. But for operators that will be very related to measurements, and then we will see why we have to use the log of an operator. Okay, we will use it very often. Okay, we can do it. Why? Because we know that these operators, they can be diagonalized. And therefore, when I calculate the function of a matrix, it will be on this it will be a matrix, okay, which will say apply this function to the eigenvalues of this matrix and then represent the matrix. So the log of A will be the log of, I will take my matrix A, its Hermitian, I can diagonalize, okay? The numbers will be real. On top of that, the sum of this will be, okay? And now I will calculate the log of A, calculating the log of the eigenvalues, and then having the same matrix. Okay? And of course, if I have a matrix when I diagonalize, okay, the diagonal, so it's diagonal, but I have eigenvalues which are negative, I cannot measure them. I cannot say the log of -8 because the log of -8 doesn't exist. Okay, so and why I say log, because we will use log because log it's a number how to count the information that we have in a state. So I will give you a state in a density matrix, say, okay, calculate the logarithmic of this is the entropy, okay, so of this state. So if it's a pure state, we will find that the entropy will be 0, which means perfect order. I know everything because it's a pure state. If it's a mixed state, which means it's mixed, so I don't know everything, I will see that the log of this state, but it's a mixed state, so it's an Hermitian operator, so I can calculate it, everything, and the eigenvalues are bigger than 1, will tell me how much ignorance I have about this state. Okay, so, and now in this, because you must be tired, you are all tired, so I want to go just a little bit fast, and I want to see that what we have done are the postulates of the quantum mechanics. So normally one starts quantum mechanics saying the postulates are these 7, and then construct quantum mechanics. But here we have done it the other way around, okay, saying that states, but it's the postulates. So the second postulate normally what says that any physical observable property, okay, is given, it has nothing to do with the measure, it's given by an operator which is Hermitian or outward joint. Okay? And of course, this operator, since A is equal to A dagger, it acts in the same Hilbert space. So it takes state psi and transform it into a state psi prime, which lives in the same Hilbert space. An Hermitian operator full cannot change. Okay? It cannot change, no, because if I do, I have my state psi. Okay. And now I apply my operator and I go to A psi, which lives, imagine that lives in a different Hilbert space. Okay. When I apply A data, which because so in this case will be like applying the opposite, I will not be able to go back my state. So, and now the last thing that we have to do is, so we have say that we have states, we have transformations, and we have to measure. Okay. And measurement is a little bit different of what we learn normally in the courses of quantum mechanics. And I will explain you why. So there is projective measurements, but there is, okay, and which are related to observed quantities. But normally in quantum information, we never talk about these projective measurements. We always talk about POVMs. Okay, this is the most general measurement that we can do in quantum mechanics, which for some reasons it's, well, now maybe they are starting to be explaining in the books of quantum mechanics, but normally they are not. So this is something that we all know, which is what does it tell us quantum mechanics? Okay, the axioms, the postulates. It says if I have a system which is in a given psi, okay, and I apply a set of operators, then we talk about probabilities. So this is one of the big things of quantum mechanics. No? Quantum mechanics, it's deterministic, so we have to talk always about probabilities. Okay, so there is no way we can guess the output in general, okay, unless we are in. So the probability that I get the outcome K, okay, so this is even my psi, which is the probability that when I measure NK, I get the output K, it's given by that, okay? So it's I apply my operator over K, I change my state, I project with the graph corresponding, okay, and this gives me my probability. And since this is the same vector, okay, it's like if I was doing the scalar product, okay, of the same vector, so the length of this new, okay, this has to be real. If I have a density matrix, it's the bond mode, this is the same. And after the measurement, what do we have? So after the measurement, I have changed my state to P prime, okay, psi prime, which is apply my measurement, and then I have to divide it by the square root of the probability because the state has to be normalized. So this is the typical standard thing of quantum mechanics, okay? And now how do we understand that? Well, we will understand that there are two kinds of measurements, okay? A set of operators, we call that they are projective measurements or positive value measurements, if these operators fulfill that they are projectors, okay? So Mi Mj, it's equal to Mi or Mj if they are equal, and if not, it's zero. This is a projector. And they are positive. Okay, so this is the typical thing that we learn in quantum mechanics. But what we do, this is not the most general operator. The most general operator is what is called a POVM. Okay, and I want to explain you what it is. Forget about the mathematics. Because quantum mechanics tell us that I can have states which are entangled. Okay, I can correlate one system with another. So imagine that I have an atom here, and I correlate this atom with another atom. Okay. So there is a possibility that I get information about this one, measuring this one to here. Okay. There is possibility. Why not? No. So it's. I mean, in some way, it also happens between us. No. So if classically, it also happens. No. Imagine that we want to learn something in an indirect way. No. So I don't know how to explain it now. But we have correlations. Well, yeah, it's very easy. For instance, no, I'm giving this course. I'm giving this course here. Yeah, sorry. Okay, and there is a clear correlation. Okay, because this is in Rwanda, so there is a clear correlation that if I look to one of the students, I expect that most of the other students also will be from the area. I don't have to measure all of them. This will be a correlation. Saying measuring something, I learn about other things. Okay, and in quantum mechanics, this is what we do all the time. Okay, so we can think that I want to measure properties of an atom. This atom maybe is entangled with another system. Okay, I measure on the big space, and I will get some information about the system. Okay, so it sounds pretty reasonable, and it's something like that. I have a state. So if I want to distinguish between these two things, it's like, imagine that I have my system A, and then if I have my system A and it's isolated, the only thing that I can look at that, the only thing that I can do on this system, if it's isolated, is to do projective measurements. Okay, but imagine that I have A which is related with B. Okay. And now imagine that I do in this, which is isolated, projective measurements in AB. Okay, so these projected measurements in AB are equivalent to something that we call POVM on E. Okay, I will learn something on E. Yeah, this is what it's called, POVM. Okay, so what is a POVM? Well, we have to define mathematically. But physically, I would like that you understand. Okay, so it's like if I was making a projective measurement in a bigger space where my system is, and then getting information from that. Of course, if in this bigger space, okay, this A and B, they are not correlated, I can measure it the biggest, that I will not get any information extra. Okay, only when there is correlations, I can have extra information. So these operators, we say that a collection of operators is a POVM if they are positive, and the sum, okay, of these operators is the matrix identity. Okay. This is what is important. And we can understand always this POVM like a projective measurement in a Hilbert space. Okay. So it's different, okay? So it looks like, oh, what is that? Quantum mechanics always tells me that the only thing that I can learn about that system is an observable I can diagonalize because, and then I have my operators, which are projectors. Yes, this is true, but I can do POVM. So for instance, if I have a finite dimension 2, okay, any operator which acts in dimension 2 in a qubit, okay, will have as maximum 2 projectors because it's this dimension. I diagonalize a matrix of 2 by 2, and I will have 2 eigenvectors, which are projectors, and 2 eigenvalues. I will not have 25. Okay, but if I do POVMs, I can have many. I can have infinite. No, so for instance, let me put an example which is easier. Okay, imagine that I put the following: a POVM, which is this E of theta, which is this operator, which it's given by this matrix. Okay, which is the measurement that I am applying to that. Okay, this measurement is M of theta. Okay, which is, so it comes from here. Okay, it's the square root of this. It's very unpleasant, but it's like that, where E of theta is just a superposition of this qubit. So I have my qubit on state 0 plus a phase on the state 1. Okay. Now, this E of theta, they are always positive for any theta. Okay, so, and the sum of them for theta going from 0 to infinite, it's equal to the identity. So it's a POVM. And which corresponds to that? This corresponds to measuring, okay, on this Hilbert space, okay, this equatorial plane, which is infinite systems, which is the one that I have drawn here. So these are 2 different things. A projective measurement of a qubit, I can only have 2 projectors, okay, 2 operators, 2 measurement operators. While in a POVM, I can have infinite if I want. Okay, and now here quantum mechanics has to be very funny because everything has to be different, okay, of our intuition. So I have these measurements, so they can be P's or POVMs, it doesn't matter. And now I say, okay, how are sequential nodes? Now let's play with these things because this is what we are going to do all the time. Extract the things of quantum mechanics which are funny. So imagine that I have my state psi and I want to measure P and Q, which are 2 observables. And now I want to know, okay, which is the result of measuring that. Oops. Okay, and let's start by the first case, okay? So I'm asking, which is the probability that when I do that on my state, so I have a measurement, which is an operator P, and then another measurement, which is Q, and I want to say, which is the probability, okay, that I got, sorry, I think I mix, okay. So which is the probability? Well, I have to use quantum mechanics, okay? So I'm asking, which is the probability that when I have measured P, I obtain A? Okay, and I calculate it because I know how is the postulate 3, and I just have to look at that. And then I ask, and which is the probability that when I have measured P, I obtain E, and when I measure Q, I obtain B? And this is a conditional probability, okay? And this is what I'm writing. The probability of obtaining A and B is the probability. I have to read always from the right. The probability that when I was measuring my observable P, I obtain the output A. And then with this state, I measure Q, and conditional that I get A, I will have B. And this is exactly this expression of here. Is the expectation value of psi, where I have PA, QB, PA. And now, sorry?
Why did you have QB?
Why I have PQP?
Why did you have QB? Why did you just QB?
Because I say, listen, my experiment that I want to see here is, I want to know which is the probability in one case, okay? That, well, in both cases, I mean, this is how it's quantum mechanics. In both cases, I want to measure P, and from P, imagine that P is the spin, okay? I want to obtain spin up, okay? And now I want to measure B, that can be also the spin after that, okay, in another direction, and I want to obtain B, okay? I apply this, and then I take PA, QB, PA, because this is the, of all the operator PA, I'm going to get, of all the operator P, I'm going to get PA, so P will be written like that. I will put that sum over A, that it's 2 dimension, let's say PA plus BPD. Okay, it's an omission operator and I diagonalize. So the probability of getting A will be given by PA. And now I have to measure, once that has happened, I want to measure Q. And the probability that Q, which is another operator, gives me B, okay, will be exactly this expectation value. It's just quantum mechanics, right? And now I want to do it the other way around. Okay, I say, no, let's do the same, but first I measure Q and then I measure P. Okay, and I want that measuring Q gives me B and measuring P gives me A. Okay, so the same outputs. Well, of course, the result is not the same. Okay? The result is not the same, and it only be the same if these operators commute. And this is what quantum mechanics is so tricky, okay? Because measuring, well, this is what quantum mechanics tell us, no? Quantum mechanics tell us that if I want to measure which is the surface of this table that I have in front, if I measure first, which is the length and then the width, it's not the same that if I measure first the width and then the length. This is very strange, but it's like that. So we know, and this is what quantum mechanics is telling us. So, and these two things will be in classical mechanics, this is impossible because operators, they commute, but in quantum mechanics, they do not commute. Okay? So it's not the same to measure first one thing unless the two operators commute. So if, for instance, P is measuring sigma x, and so the spin along the x direction, and Q and having up or down along the x direction, and Q is measuring the spin along the z direction, well, these two things, they do not commute. We know that sigma x, sigma y, they will not commute, okay? So it will not be the same. So when we do these things, the one has to be BB, yes, QB, PA, QB, sorry, excuse me, yes. Okay. So how do, well, so let's put it, no, I just wanted to write an example. So imagine that I have my initial state, it's the 0, okay, more simple impossible. Q, it's projecting on the superspace 0 or 1. I want to know if the Q is enter on 0 or 1. And Q, it's projecting on the X and so plus minus, which is the eigenvalues of sigma x. It's like measuring sigma x. It's the same. Okay. And now I start. And these are the chain probabilities, okay, of PAB and of PPA. And you see they are very different. Okay, so the probability, for instance, that on P I observe 1 is 0 because I have started with my state on 0. So when I measure P, it has to be 0. Okay, so A1 is impossible. And so these are completely different probabilities. Okay, so that means that the measurements, they do not commute, and they are very tricky. And this is very tricky. So this is one of the things which is very difficult. So one of the things that one has to do in quantum information is think which are the optimal measurements to obtain the maximum information that you have. Okay, optimized measurements. This is one of the most important things. In quantum information, everything is optimizing. Okay, optimize performance, optimize measurements, optimize preparation, optimize. So this is, it's an optimization problem. Okay, and then obviously you can have composite systems, which says, okay, I have 2 identical copies of my system. I prepare 2 identical copies of my system. In one of them, I measure P. In the other one, I measure Q. Well, if these guys, they don't speak to each other, then the probability of having AB will be obviously the same that the probability of having BA. Doesn't matter if I first measure Q, and then in my first copy, I measure Q, and later in my second copy, I measure Q, P. or the other way around. Okay, so this is exactly the same. Okay, so I think I will stop here. It's already, so if there is any question or something, it's already a lot of material. And although I wanted to finish all these things in order to do quantum computation with more detail. So I don't know if there is any comment or question. You maybe have access better than me. If there is some comment or. I'm sorry, because. Okay, that's fine. Okay, so if this is not the case, then I think we will stop. And next week we will start to ask things about, yes.
Is it possible by sufficient and the operator is unitary when I'm giving an operator and a state? We are measuring not the operator is not important. Is it possible to tell the operator is unitary by action?
Well, I mean, yes. So for instance, of course, an operator, if it's unitary, will never change the length of the state. Okay. But if I give you an operator which is not unitary, so this also means to be unitary. So if I have a vector of length 1, after a unitary operator, it's of length 1. So, and then you can say, what happens? So let's imagine a state, an evolution which is not unitary. Okay. So I say quantum mechanics tells me that if I have an evolution of a state, whatever state it is, I have my hydrogen atom. Okay. And I want to see, I read it now. Okay, tomorrow morning I want to see how is my hydrogen atom. Okay, I have it doubles. And then I will say that, okay, this hydrogen atom is under something, but it's isolated. So it has a Hamiltonian, so this hydrogen atom will have Hamiltonian, which is T square over square plus the potential or the electron, which is there. Okay. And then I say, oh, yes, I mean, I will see how it is this hydrogen atom. How is the electron of this hydrogen atom? Let's put it like that. I'm going to do a measurement. Okay. And then I will see that, okay, it corresponds to unitary, which is E to minus C, the Hamiltonian times T, the T times the and fantastic. But if it's not unitary, which means that my hydrogen atom is in interaction with other atoms. Okay. And now I look at the electron of this hydrogen atom. I close it in a box and I thought that this box was happy, but in this box there are other atoms. There are collisions and so on. Now I measure, okay? And what I will find? Well, I will find that I don't have any more a knowledge of this state, because physically I will not be able to describe my electron of the hydrogen atom with a pure state. Okay? It will be a density matrix. And if on this density matrix I want to find, so I will see already that this is not unitary without knowing what has happened. Okay? Because when I do, so one has to think that when I have a pure state, in quantum mechanics, sometimes you say we know everything about the state, and it's true, because if I have a pure state, okay, and now I apply some measurement operator, whatever it is, I know which probability I will get some output. But if it's not a pure state, I don't know that. So I will be able to know if this electron has evolved according to without knowing which is the evolution operator. If it was unitary or not, I would be able in some cases, yes. You can do it.